Hi there. Today I'll describe our work on testing the safety of self-driving vehicles by simulating perception and prediction. Self-driving cars are coming, but before we can safely deploy them at scale, we need to test and verify their safety. A natural way to do this is to directly test a car in real traffic. Although this approach gives us the best realism, it's not possible to perform repeatable structured tests here, especially for safety-critical scenarios. Moreover, it is difficult to scale this approach. Alternatively, we can test the cars at a test track instead. This approach gives us repeatable, high-fidelity structured tests. However, it is still difficult to scale this approach to the amount of testing necessary for safety verification. As a result, most self-driving companies today complement real-world testing with computer simulation. Although we lose some of the fidelity of testing in the real world, simulation allows us to scalably test our self-driving cars to millions of miles per day. Today we'll describe a novel approach to testing and simulation that tries to narrow this gap in realism while retaining simulation's nice scaling properties. Now before we dig deeper, let's review how a self-driving car works. Typically, the autonomy stack of a self-driving car is composed of a cascade of modules: perception, prediction, and motion planning. At each time step, the perception module takes raw sensor data and an HD map as input and outputs bounding box detections. The prediction module then forecasts the future locations for each detected actor. Finally, the motion planner takes these intermediate perception and prediction outputs and generates a safe trajectory for the self-driving car. There are many ways to implement these modules. For example, in our experiments, we implement the perception and prediction modules with PnP a joint perception and prediction model. And for our motion planner, we use the learnable PLT motion planner. Now, given the stack, a common way to test it in simulation is to mock the self-driving car's intermediate outputs with perfect perception and prediction. To this end, test engineers will create test scenarios by drawing bounding boxes and trajectories for each actor in the scene. This is a very simple way to test motion planning at scale, and it provides an important upper bound on the performance of the vehicle. However, the mocked objects used here don't reflect the noise present in real systems, thus limiting the realism of these tests. An alternative approach is to use sensor simulation instead. This approach allows us to test the full autonomy stack end-to-end. However, existing methods can be difficult to scale, have large domain gaps, or focus on just one of the many sensors used by self-driving cars. These limitations make sensor simulation a very exciting area of research, but one that is still unable to meet all the requirements of real-world systems. In this work, we propose to directly simulate the self-driving car's perception and prediction outputs instead. We call this task perception and prediction simulation, or PnP simulation in short. In contrast to using perfect perception and prediction, PnP simulation can be used to realistically test motion planning. And in contrast to sensor simulation, PnP simulation is simple and cheap to scale. Our system takes a very simple scene representation as input. Starting from a high-definition map, test engineers can sketch a test scenario by drawing bounding boxes for each actor in the scene, and then drawing trajectories for each actor to indicate its positions over time. The simplicity of the scene representation means that it can be easily sketched in a matter of minutes. Furthermore, test engineers don't need to start from scratch. They can start from previously sketched scenarios, or even from existing ones from labeled datasets. And this makes our overall process even faster. Now, given the scene representation, our idea is to design a simulation model that takes this as input and produces noisy outputs similar to those of the real perception and prediction system. Then to test the motion planner, we can simply mock the real system's outputs with our simulated ones. The key question now is, how do we design a PnP simulation model? As a first step, we can start by simply modeling no noise. That is, we assume perfect perception and prediction. As we mentioned earlier, this approach gives us an important upper bound on the motion planner's performance, but falls short in terms of realism. To make things a bit more concrete, let's take a look at some experiment results. Here we show perception, prediction, and motion planning metrics that quantify the similarity between our simulations and the outputs of the real system. On the left, we have average precision, so higher is better here. In the middle, we have prediction final displacement error, so lower is better. And on the right, we have the final displacement error between the motion planner's trajectories when given real perception and prediction outputs versus our simulated ones, so lower is better. As shown in these three plots, there is quite a gap in realism when assuming no noise. So what if we used random noise instead? And in particular, we can use noise from a Gaussian distribution to perturb each actor's bounding box and trajectory, and noise from a Bernoulli distribution to simulate misdetections. This is similar to what researchers have done in domain randomization for training agents in simulation. However, our goal here is to test agents in simulation instead. Unfortunately, things get worse across the board. And in particular, we can't even compute prediction metrics here because recall is too low. Part of the problem is that the Gaussian distribution is insufficiently expressive to capture the noise of a real system. So what if we use the Gaussian mixture model instead? Things get a bit better in terms of perception now, but overall, this approach still underperforms the no-noise method. The issue with these simple noise models is that they don't account for interactor variability. Therefore, in this next approach, we explicitly model interactor variability by training an MLP to predict noise conditioned on per actor features. And as shown here, our simulation fidelity improves significantly. Still, all of the models we've discussed so far don't take scene context into account, which should intuitively correlate with the success of the real system. To address this, in our next approach, we designed a convolutional neural network that exploits scene context to improve PnP simulation. Our model takes 3 input representations to capture scene context. First, a sequence of occupancy mass representing each actor's bounding box in the past, present, and future. Second, a series of binary images encoding a high-definition map of the scene. And finally, a sequence of constant horizon occlusion mass to approximate sensor occlusion in the scene. Next, these features are run through a shared backbone feature extractor. Then we use a lightweight perception head to simulate the bounding box outputs of the real system. And we use a simple prediction head to simulate the trajectory predictions as well. By combining the outputs of these 2 heads, we have our final PnP simulations. And our entire system is trained end-to-end using supervision from the real system. As we would expect, incorporating scene context significantly improves simulation fidelity. In particular, we get a 45% relative improvement in perception simulation fidelity versus no noise. We also get a 39% relative improvement in prediction fidelity. And as a result, we can nearly double motion planning realism as well. Now let's take a look at some qualitative results. Here we visualize perception, prediction, and motion planning outputs for 1 frame in each scenario. On the left, we show the real outputs, and on the right, we show our simulations. We use black boxes to denote perfect perception and prediction outputs, and a blue box to show the motion planner's trajectory when given these as inputs. We also use purple boxes to denote real and simulated perception and prediction outputs, and the red box shows the motion planner's trajectory when given either of these as inputs. So from this side-by-side comparison, we can see that our simulations closely match real perception and prediction outputs. In particular, we can simulate mispredictions due to multimodality, as well as misdetections due to occlusions. Using our simulated outputs, we can also identify scenarios in which the motion planner causes a collision, as we show here. Here is another example of a collision scenario that we have successfully identified in simulation. Finally, we show an example where the motion planner chooses to lane change when given either real or simulated perception and prediction. In contrast, it chooses to go straight instead when given perfect perception and prediction. In summary, we have introduced the novel task of perception and prediction simulation. We benchmarked a variety of noise models and showed that scene context is essential for achieving high simulation fidelity. Finally, we demonstrated that PnP simulation can be used to realistically yet scalably test motion planning. We hope our results here will inspire more work in this important field so that one day we can certify the safety of self-driving cars and deploy them at scale. Thanks.